Welcome back to College Algebra. In this video, we're going to be looking at the graphs of the logarithmic functions. This is section 6.4, immediately following the section just about logarithmic functions. So, as we get going, we are going to look at what these graphs look like and how we can plot them or determine, based on a graph, which logarithmic function we're looking at. So, a little bit of encouragement before we get started. Commit to the Lord whatever you do, and He will establish your plans. Proverbs 16:3. Whatever you do is a pretty all-encompassing encouragement of whether what you're doing is graphing logarithmic functions, or helping a friend in need, or taking care of somebody that you are taking care of right now, whether that's financially or emotionally or supportively. Committing to the Lord in whatever you're doing will establish your plans. And I just think that's a good encouragement for all of us to do, even if that thing we're doing is graphing logarithmic functions. So the first thing, before we even look at the graph of the logarithmic function, is to say, hey, we've got a new rule. So Domain in the past brought up two rules. Domain brought up the rule where if you had a 0 on the bottom, that was bad. You could not equal 0 on the bottom. So if you just had some number, you can't have the bottom be 0. It also said if you had a square root, the inside had to be greater than or equal to 0. Just the inside, not the whole square root itself. And we have a third one now. Logarithms introduce a third one where it's a little bit different. If you have a log, just for logs or natural logs, if you have either a log or a natural log, the inside, just like with square roots, has to be greater than 0. So it's even stricter than square roots. We don't, and we'll see that in a second when we graph our asymptote, but it can't even be 0. We cut it off right at 0 and go on. So that being said, what's the domain of this f of x right here? Well, we just take the inside and we say x minus 2 has to be greater than 0, which means x has to be greater than 2, which means our domain is 2 to infinity. Oh, but not including 2 because it doesn't have the underline underneath it. So it's different than square roots in that way, where we don't include the value that we're stopping at. So in a similar manner, this one would be 5 to infinity. And if you want to take a pause and work that out and make sure we're right, you can. And now we're about to see why. Why can't it include that boundary condition? Well, so if you look right here at this graph, the blue line was the exponential function that we talked about all chapter. We've talked about it with a base of 2, and it's exponentially increasing. You'll notice that blue line has a y equals 0 horizontal asymptote. Well, here's the cool thing. If you invert that equation from both sections when we talked about inverse functions, that just means you switch x and y. And so we take this, what used to be a horizontal asymptote, and we say, actually, now you're a vertical asymptote because I'm going to switch out that y for an x. And I've got a vertical asymptote at x equals 0 now. So what used to be a horizontal asymptote is now a vertical asymptote that orange line is approaching. And that orange line is the inverse of the blue function, reflected across the line y equals x. And so the basic logarithmic function looks like that orange line, where it's going to have a domain of 0 to infinity, a range of all real numbers. And you'll notice when we say all those two things, those are exactly opposites of the parent or the toolkit function of the exponential function, because we've switched x and y, which means we've switched our domain and range. And instead of a horizontal asymptote, this one has a vertical asymptote at x equals 0. And so those three tools are going to help us when we go to graph this function, the natural logarithmic function, or the logarithmic function. So here's a function. Let's graph it. The first thing I see is there's really no shift happening to it, and so I'm just going to go ahead and assume, without plotting any points, that we have an x equals 0 vertical asymptote. But let's find out by plugging and chugging a few points. Okay, the first point I'm going to plug in, and my favorite point to always plug in for log, is 1. And you'll see why in a second. Because if you plug in 1, you get the log of 1 over 5 of 1 equals what? You're like, okay, well, let me think about this for a second and convert the log to an exponential. 1/5 to the what equals 1. And 1/5 to the 0 is the only answer you can have. And so we need a 0 up there. 1/5 to the 0 equals 1. Remember that little trick from the last video I showed you? You can just think about this as a 1/5 to the what equals 1 would be the answer of that logarithmic equation. And so the log base 1/5 of 1 equals 0. And we plot the point 1, 0. So far, so good. We're on one side of our asymptote. Everything's great. Let's try 1/5, because this is another pretty easy one to plug and chug. Log base 1/5 of 1/5 equals, and like I said, we're just going to rewrite it as 1/5 to the what equals 1/5. And that should be a pretty quick recognizable fact. Anything to the first power equals itself, and so that just spits us out 1. And so we have another point, a little harder to graph, but we go to like 1/5, 1, and we graph it. And if we connect those two dots, we can see where it starts to approach our asymptote. And we probably need one more point, so I'm going to try 5. I'm going to say 5, and we'll say log 1/5 to the what, or to the of 5 equals. And again, that exponential function is you take the base and you write 1/5 to the what equals 5. And this is where our exponential properties are really important to master. So if you need to practice them, go back and hunt down some exponential worksheets, whether it's from a high school course or anything you can find that can help you learn exponential properties. Because the way you get that 5 from the bottom to the top is you raise it by -1. And so our output is -1 if we go all the way to 5. And that checks out with our function, because we need to go all the way over to 5 and down 1. And that looks like it stayed all on the same side of the asymptote. And so let's look real quick about our range. How high up does it go? It looks like it goes up forever. How far down does it go? It looks like it goes down forever. And so our range is all real numbers. And our domain, it looks like it starts at 0, never touches it, and then goes to infinity. We could have also found that domain pretty quick by applying that property we just learned, where you take the inside, you say the inside has to be greater than 0, and there's that same domain. And so there's some practical skills, whether it's plugging and chugging points or identifying key features of the graph, to get this logarithmic function onto a graph. We've got another one. Let me see how many we got. Not too many. We've got another one where the only thing that's happened to this function is it shifted up by 4. And so I'm going to try to just pick some pretty numbers to plug and chug. I know this is a little a weird way to do it, but once you get used to the feeling of plugging and chugging numbers into a log, you might not have to rewrite it every single time. You might be able to start remembering key facts about it. So for instance, if I plug in -1 into my equation, I get log base 3 of -1 plus 4, which is log base 3 of 3. And maybe without rewriting it, you could think a little bit and say 3 to the what equals 3, and you could get a 1 back as your answer, -1, 1. And then we should probably pick a few more points to plug and chug. What do you think about 5? If you plug in 5, you get the equation log base 3 of 9. And you ask yourself the question, 3 to the what equals 9? And your answer is 2. And so we have the point 5, 2. That's, 5, 2. And then last but not least, we're going to have a point to plug and chug, which is log 3 of negative 3. Or log 3 of negative 3 plus 4, which would be log 3 of 1, which would just be 0. And so if you plug and chug negative 3, it'll kick you out with the 0. So we get the point negative 3, comma, 0. And what I see pretty fast is at the very beginning of the problem, somebody might have been yelling it at the very beginning, and then I just moved on and didn't even think about it. When I read this equation, you might have been saying, that's not up, that's to the left, because it's on the inside. And you would have been right, and we would have seen that as soon as we plugged these points in, and we would have said, this is a horizontal shift to the left by 4. And so if you originally had a horizontal asymptote at x equals 0, I'm just going to move it over 4 and say, there's my new horizontal asymptote at x equals negative 4. And if I connect my dots for the rest of the problem, it should look like that logarithmic function that we've been seeing come up all day. And so what I think the hardest thing to do here is picking the right points to plug and chug to really see this function come alive. A few helpful hints for that are log base b of 1 is always 0, because anything to the 0 equals 1. Log base b of b is always 1, because anything to the first power is itself. And so those are two little hints to kind of get you moving and trying to pick the right numbers to plug and chug. All right, this one's going to be pretty similar, just to shift up 2. This time it's actually up 2. And I'll leave you to try that by yourself because it's not too crazy of a shift. Try that one on your own. You can pause the video and work on it. You can go look at the completed notes to get a solution to see how close you were. And you can practice that example. And so, real quick before we wrap up for this section, I want to just ask a quick conceptual question that might be a little bit easier without graphing the function, and say, what is the vertical asymptote of this natural logarithmic function? And so for the vertical asymptote to get applied, we probably should know a little bit about what the function originally looked like before the shift happened. And remember, this function had a vertical asymptote at x equals 0. And the logarithmic function looked like this. Now, if we have a function that looks like that with a vertical asymptote of x equals 0, shifting it up or down doesn't affect the vertical asymptote. So even though it gets shifted up by 3, that has no bearing on the asymptote itself. But what does affect it is this to the right by 1 that happens on the inside of the logarithmic function. And so that asymptote will shift to the right by 1, and it'll bring the whole graph to the right by 1 with it. So your original horizontal asymptote was x equals 0. Your new vertical asymptote is going to be x is equal to positive 1. So if we wanted to graph that on this graph, we would just go over to 1 and draw a new asymptote right there at x equals 1 and sketch a new function that approaches that asymptote and is just shifted over by 1. And then we could shift it up by 3 if we wanted to finish the problem, 1, 2, 3, and go up by 3 and say that red line is f of x, where the black line was the original function, which was the natural log of x, and the blue line was the application of the first horizontal shift, which was the natural log of x minus 1. And so we moved it over 1 on the blue line and up 3 with the red line. But all of that was not essential for us to use characteristics of the graph to identify the vertical asymptote in the first place, which was just x equals 1, because it started at x equals 0 and moved over 1 to the right. All right, so that's some basics of graphing logarithmic functions. As we get closer and closer to the end of this chapter, I'd encourage you to go back and study everything you can to prepare for the chapter exam. Thanks for watching, and I'll see you next time.